Most people think they know what is inside a galaxy. Stars, right? Billions of stars scattered through space. But that is only what you can see. Tonight, I am going to show you what has been hidden there all along, right in front of us, invisible to every photograph you have ever seen. You can relax completely now. Let your body settle. Let your breathing slow. Because where we're going, there is no rush, no urgency, no deadlines. Galaxies measure time in millions of years. A single rotation takes longer than dinosaurs walked the Earth. We have all the time we need. So close your eyes if you wish, get comfortable, and let us begin this gentle drift together into the hidden heart of galaxies. The quiet heart of spiral arms. When you look at a picture of a spiral galaxy, you see the bright arms sweeping outward like cream stirred into coffee. But these arms are not solid structures. They are more like waves moving through water. Gentle ripples in the fabric of stars and gas that travel around the galactic center, patient and unhurried. Inside these spiral arms, there is so much empty space. If you could stand on a planet within one of these arms, you would see individual stars scattered across the darkness, separated by distances so vast that light itself takes years to cross from one to the next. For light years to the nearest star, 10 light years to another cluster, 20 light years to a small nebula glowing softly in the distance. That is about 20 trillion miles of quiet darkness between each point of light. The stars within a spiral arm are not fixed in place. They are all moving, drifting along their own orbital paths around the galactic center. Some move a little faster. Some move a little slower. But together, they create this impression of structure, this beautiful spiral pattern that persists even as individual stars come and go. Think of it like cars on a highway at night. From far above, you would see the pattern of headlights and taillights flowing along the road. But the individual cars are always changing. Some exit. Some merge. New ones join the flow. The pattern remains even though the participants are constantly moving through it. In the same way, spiral arms are not made of the same stars year after year. They are density waves, regions where stars and gas happen to bunch up slightly as they orbit. A star might spend a few million years passing through a spiral arm, then continue on into the quieter spaces between the arms, then eventually pass through another arm millions of years later. This means that most stars, most of the time, exist in the spaces between the spiral arms. In the calmer regions where the density is lower and the pace of life is gentler still. Our own sun lives in such a space, in a minor spur between two major arms of the Milky Way. A quiet neighborhood on the outskirts of the cosmic city. The spiral arms themselves rotate around the galaxy, but not like a solid wheel. They move at their own speed, different from the speed of the stars. This is called a pattern speed. The arms are more like a wave moving through a crowd, where the wave travels but the people stay mostly in place, just bobbing up and down as it passes. And so the galaxy turns, slowly, majestically. One complete rotation takes about 200 million years. The sun has only completed about 20 or 25 orbits since it formed. Everything here moves on timescales that dwarf human experience. There is no rush. No urgency. Just the slow, steady turning of billions of stars around a common center. Ancient light and stellar nurseries. Hidden within the spiral arms and scattered throughout galaxies are clouds. Vast clouds of gas and dust, some of them spanning hundreds of light years across. These are the stellar nurseries, the birthplaces of new stars, though birth is perhaps too quick a word for what happens here. These clouds are made mostly of hydrogen, the simplest and most abundant element in the universe. Mixed in with the hydrogen are traces of helium and tiny amounts of heavier elements. Carbon, oxygen, silicon, iron. The remnants of ancient stars that lived and died long ago, scattering their enriched material back into space. The clouds are cold. Very cold. Only a few degrees above absolute zero, that ultimate coldness where even atoms barely move. In this frigid environment, the gas begins to clump together, drawn by its own weak gravity. Slowly, over hundreds of thousands of years, these clumps grow denser and denser. Imagine a region of space where the gas is just slightly thicker than the space around it. Gravity pulls more gas toward this region. As more gas accumulates, the gravity grows stronger. More gas falls in. The process feeds itself, gently, patiently, over timescales so long that entire human civilizations could rise and fall in the time it takes for a single star to begin forming. Deep inside these collapsing clouds, in the densest regions, the pressure begins to build. The temperature starts to rise, degree by degree, as the weight of all that gas presses down on the core. After a million years of slow collapse, the center of the cloud becomes hot enough for something remarkable to happen. Hydrogen atoms begin to fuse together, forming helium and releasing tremendous amounts of energy. A star ignites. Not with a dramatic explosion, but with a gentle warming, a soft brightening that grows over thousands of years. The star begins to shine, pushing back against the gravity that formed it. The inward collapse stops. Balance is achieved. The star settles into a long, stable life that may last billions of years. But the star is not born alone. The cloud that formed it was vast, containing enough material for hundreds or thousands of stars. All across the cloud, in different regions, other stars are forming at the same time. The result is a cluster, a family of stars born from the same parent cloud, all roughly the same age. These stellar nurseries glow softly in infrared light, hidden from visible light telescopes by the dust that surrounds them. But infrared can penetrate the dust, revealing the warm cocoons where baby stars are growing. If you could see in infrared, galaxies would look very different. The spiral arms would glow brightly with the heat of star formation, while older regions would appear dimmer and cooler. Most of the gas in a galaxy exists in these clouds, waiting patiently for gravity to do its slow work. In between the clouds, the gas is thinner, more diffuse, spread out across vast distances. This is the interstellar medium, the sea through which all stars swim. And so galaxies are constantly recycling their material. Old stars die, returning gas to space. New stars form from this gas. Planets form around the stars. Eventually, those stars too will die, and the cycle will continue. It is a slow, gentle rhythm that has persisted for billions of years. The invisible ocean of dark matter. There is something else hidden inside galaxies. Something that does not shine. Something that does not emit or absorb light. Something we have never directly seen, but know must be there because of how it affects everything around it. We call it dark matter, though that name is more of a placeholder than a description. We do not know what it is made of. We only know that it exists because galaxies behave in ways they should not, unless there is much more mass present than we can see. When astronomers measure how fast stars orbit around the center of a galaxy, they find something strange. The stars far from the center move too quickly. According to the laws of gravity, stars on the outer edges of a galaxy should orbit more slowly, just as the outer planets in our solar system orbit more slowly than the inner planets. But galactic stars do not follow this pattern. Stars at the edge of a galaxy orbit at nearly the same speed as stars closer to the center. This should not be possible unless there is additional mass present, mass we cannot see, extending far beyond the visible edge of the galaxy. This invisible mass, this dark matter, appears to surround galaxies in vast spherical halos. These halos extend far beyond the stars, reaching out hundreds of thousands of light years into space. In fact, most of the mass of a galaxy is not in its stars at all. It is in this dark matter halo, this invisible ocean in which the visible galaxy floats like an island in a dark sea. Dark matter does not interact with light in any way. Photons pass right through it as if it were not there. But dark matter does interact through gravity, and gravity is enough. Gravity is what holds galaxies together. Gravity is what keeps stars in their orbits. Gravity is what allows galaxies to form in the first place. Without dark matter, galaxies as we know them could not exist. The stars would orbit too quickly and fly apart. The gravity from visible matter alone would not be strong enough to hold everything together. Dark matter provides the additional gravitational glue that keeps galaxies intact. Scientists have proposed many ideas about what dark matter might be. Perhaps it is made of particles we have not yet discovered. Perhaps it is a type of matter that exists in a realm beyond our normal perception. Perhaps it is something even stranger. For now, It remains one of the great mysteries of the universe. But the mystery does not diminish the wonder of it. There is something beautiful about knowing that galaxies are surrounded by this invisible presence. Like a gentle hand supporting everything, unseen but always there. Dark matter does not shine, does not call attention to itself. It simply exists, quietly doing its work, holding the cosmos together in its patient embrace. Every star in a galaxy is embedded in this dark matter halo. Every planet, every particle of dust. We ourselves, here on Earth, are surrounded by dark matter right now. It passes through us constantly, billions of particles every second, interacting so weakly that we never notice. We are swimming in an invisible ocean, and we always have been. It is humbling to realize how much of the universe is hidden from our direct view. We see the stars. We see the glowing gas. We see the bright galaxies scattered across the sky. But all of that visible matter makes up less than 20% of the total mass. The rest is dark matter, invisible and mysterious, forming the scaffolding upon which all visible structures are built. Wandering stars and orphan worlds. Not all stars in a galaxy follow predictable orbits. Some are wanderers, traveling on paths that take them far from the galactic plane, out into the dark space between the spiral arms, or even beyond the visible edge of the galaxy itself. These rogue stars have been flung from their original locations by gravitational encounters. Perhaps two stars passed close to each other, and the interaction boosted one star to a higher velocity, sending it on an eccentric orbit. Perhaps a star cluster dissolved over time, and some of its members were scattered outward like dandelion seeds on the wind. These wandering stars move through regions of space where other stars are rare. If a planet orbited one of these rogue stars, and if someone stood on that planet looking up at the night sky, they would see very few stars. The galaxy itself would appear as a distant, faint glow, far away across a vast darkness. It would be a lonely place, beautiful in its solitude. Some stars are ejected from galaxies entirely, thrown out by close encounters with the supermassive black hole at the galactic center, or by interactions with other stars in dense clusters. These hypervelocity stars travel at incredible speeds, millions of miles per hour, racing out into the space between galaxies. They will never return. They are truly orphaned, destined to wander the cosmic voids for billions of years. And then there are worlds without stars. Planets that have been ejected from their solar systems, cast out into the darkness by gravitational interactions with other planets or passing stars. These rogue planets drift alone through the galaxy, untethered to any sun. We do not know how many rogue planets exist, but some estimates suggest there could be billions of them in our galaxy alone. Perhaps even more rogue planets than stars. They are nearly impossible to detect because they emit almost no light and no heat. They are cold, dark, silent worlds moving through the emptiness. A rogue planet would be a strange place indeed. With no sun to warm it, the surface would be frozen, locked in perpetual darkness. Any atmosphere it once had would have frozen and fallen to the surface as snow. The only light would come from the faint glow of distant stars, too far away to provide any warmth. Yet even in such extreme cold, there might be warmth deep underground. The planet's interior could still be hot from the heat of its formation, or from radioactive decay of elements in its core. If the planet had oceans once, those oceans might survive beneath a thick layer of ice, kept liquid by heat rising from below. In such hidden oceans, sheltered from the cold and darkness of space, life might even be possible. These wandering worlds and orphan stars remind us that galaxies are not static structures. They are dynamic, chaotic, full of objects moving on unexpected paths. Some stars will complete their orbits in the galactic disk for billions of years. Others will wander far afield, traveling to the edges of the galaxy and back. And a few will escape entirely, becoming citizens of intergalactic space. The galaxy is vast enough to hold all these different paths. There is room for the orderly orbits and the eccentric ones. Room for the stars that stay close to home and the ones that wander far away. Everything belongs. Everything has its place in the grand, slow dance of cosmic motion. The gentle giants at the center. At the very heart of almost every large galaxy lies something both strange and quietly powerful. A supermassive black hole, a concentration of mass so dense that not even light can escape its gravitational pull. These objects contain millions or even billions of times the mass of our Sun, all compressed into a region smaller than our solar system. Despite their fearsome reputation, most supermassive black holes are remarkably peaceful. They sit quietly at the centers of their galaxies, surrounded by orbiting stars but not actively consuming material. They are like sleeping dragons, vast and powerful but still. Our own galaxy, the Milky Way, has such a black hole at its center. We have named it Sagittarius A star, and it contains about 4 million times the mass of the Sun. For most of the time, it does almost nothing. Occasionally, a gas cloud or a star wanders too close, and material begins to fall toward the black hole, heating up as it spirals inward. For a brief time, the black hole flares with light as this material is consumed. Then quiet returns. The black hole itself is not visible. The point of no return, the boundary called the event horizon, emits no light. But we can see its effects on nearby objects. Stars orbit the black hole in elliptical paths, moving faster and faster as they approach, then swinging around and retreating back into the distance. By watching these orbits over many years, astronomers have mapped out the invisible presence at the center, confirming that it is indeed a black hole. Around the black hole, packed into the central few light years of the galaxy, are millions of stars orbiting in a dense cluster. These are some of the fastest moving stars in the galaxy, whipping around the center at speeds of hundreds of miles per second. Yet even this is slow compared to the size of the galaxy. A complete orbit still takes thousands of years. This supermassive black hole likely formed in the early days of the galaxy, perhaps from the collapse of massive clouds of gas, or from the merger of many smaller black holes. As the galaxy grew, the black hole grew with it, fed by gas and stars that ventured too close. Now, billions of years later, it has reached its current size, and it continues to grow, though very slowly. In some galaxies, the central black hole is more active. Material falls toward it at a steady rate, forming a swirling disk of gas and dust that glows brilliantly. These active galactic nuclei can outshine all the stars in the galaxy combined, visible across billions of light years of space. Jets of material are sometimes launched from near the black hole, shooting out in opposite directions at nearly the speed of light, extending for hundreds of thousands of light years beyond the galaxy. But most supermassive black holes are quiescent, like ours. They have consumed most of the easily available material in their vicinity, and now they wait, patient and still, for the occasional morsel that wanders within reach. They are the anchors around which their galaxies turn, providing a gravitational center that helps maintain the structure and stability of the entire system. It is humbling to think about these objects. So massive, so powerful, yet so quiet most of the time. They are not destructive forces, despite what popular culture might suggest. They are simply part of the architecture of galaxies, as natural and necessary as the stars themselves. They shape the growth and evolution of galaxies over billions of years, regulating star formation and influencing the distribution of gas. And so at the center of our galaxy, hidden behind clouds of dust that block our view, sits this gentle giant. Turning slowly, surrounded by its core of orbiting stars, it waits in the darkness. A sleeping titan at the heart of the Milky Way. Rivers of stars and stellar streams. Galaxies are not isolated systems. Throughout their lives, they interact with their neighbors, pulling on each other gravitationally, sometimes colliding and merging. These interactions leave traces, visible as long streams of stars stretching through space. When a small galaxy passes near a larger one, the gravity of the larger galaxy begins to pull stars away from the smaller galaxy. These stolen stars do not fall immediately into the larger galaxy. Instead, they stretch out into long, thin streams, following the orbit of the original galaxy but gradually spreading along the orbital path. Over millions of years, these stellar streams spread all around the larger galaxy, forming faint arcs and loops that trace the paths of long-ago encounters. Our own Milky Way is surrounded by many such streams, the remnants of smaller galaxies it has consumed over billions of years. The most famous of these is the Sagittarius stream, named after the Sagittarius dwarf galaxy that is currently being torn apart by the Milky Way. This small galaxy has been orbiting the Milky Way for billions of years, and with each orbit, more of its stars are pulled away. Now the galaxy is almost gone, reduced to a small cluster of stars still clinging together, surrounded by a vast stream of stars that have been stripped away. If you could see the Sagittarius stream in the night sky, it would appear as a faint ribbon of stars arcing across the entire sky, wrapping around the Milky Way like a scarf. But the stars in the stream are so faint and so spread out that we need powerful telescopes to detect them. They are there, though, invisible to the eye but present in their millions, moving together along their ancient path. There are other streams as well. The Monoceros Ring, a vast circular structure of stars surrounding the Milky Way. The Orphan Stream, so named because astronomers have not yet found the galaxy that created it. The Virgo Stream and the Hercules Stream, and many others. Each one tells a story of a galaxy that came too close and was destroyed by tidal forces. These streams are clues to the history of our galaxy. By studying them, astronomers can reconstruct what happened in the past, learning about the galaxies the Milky Way has consumed, when those encounters occurred, and how the Milky Way has grown over time. It is like reading the fossil record, piecing together ancient history from the traces left behind. The process continues today. The Milky Way is still consuming smaller galaxies, still pulling them apart into streams. In about 4 billion years, our galaxy will collide with the Andromeda Galaxy, our nearest large neighbor. That collision will be a slow-motion merger, taking hundreds of millions of years to complete. The stars will not actually hit each other, there is too much empty space between them, but the galaxies will pass through each other, their shapes distorting and changing, eventually merging into a single, larger galaxy. But that is far in the future. For now, we can contemplate these stellar streams, these rivers of stars flowing through the galaxy. They are a reminder that galaxies are not static. They grow, they change, they interact. They are living systems, evolving over cosmic time. The stars in these streams are old, ancient even. They were born in other galaxies, galaxies that no longer exist. Now they belong to the Milky Way, adopted children of our galaxy, orbiting along paths that will carry them through the galactic disk and out the other side, again and again, for billions of years to come. The spaces between the stars. When we look at a galaxy, we see the stars, bright and obvious. But the space between the stars is not empty. It is filled with a thin gas, and with dust, and with magnetic fields, and with light. This is the interstellar medium, the substance of the space between stars. The gas is mostly hydrogen, spread incredibly thin. In the densest regions, there might be a few hundred atoms per cubic centimeter. That sounds like a lot, but consider that the air you are breathing right now contains about 25 billion molecules per cubic centimeter. The interstellar medium is a vacuum by Earth standards, far emptier than anything we can create in our laboratories. Yet this thin gas adds up. Spread across the entire galaxy, it contains a significant portion of the galaxy's normal matter, comparable to the mass contained in stars. This gas is the raw material for future generations of stars, waiting to be compressed by gravity into new stellar nurseries. The gas exists in different phases, depending on its temperature and density. In some regions, it is cold and relatively dense, forming clouds where stars are born. In other regions, it is warm and diffuse, heated by the light of nearby stars. And in some places, it is extremely hot, heated to millions of degrees by supernova explosions or by energy from active galactic nuclei. This hot gas is so diffuse and so energetic that it glows faintly in X-rays. Mixed in with the gas are tiny particles of dust. Not dust like you find on a shelf, but microscopic grains made of elements like carbon and silicon, formed in the atmospheres of dying stars and blown out into space. These dust grains are only a few millionths of an inch across, smaller than bacteria, smaller than viruses. Despite their small size, these dust grains have a big effect. They block visible light, making distant parts of the galaxy difficult to see. This is why we cannot see the center of the Milky Way in visible light. The dust along our line of sight absorbs the light, creating a dark band across the galactic plane. But infrared light can pass through dust more easily, so infrared telescopes can see through the haze and reveal what lies beyond. The dust also affects the formation of stars. In the cold clouds where stars are born, the dust shields the interior from outside radiation, allowing the gas to cool and collapse more efficiently. The dust also provides surfaces where molecules can form. Hydrogen atoms land on dust grains and combine to form molecular hydrogen. Other atoms combine to form water, ammonia, carbon dioxide, and more complex organic molecules. Some of these molecules are the building blocks of life. There are also magnetic fields threading through the interstellar medium. These fields are weak, far weaker than the magnetic field of Earth, but they extend across vast distances. They guide the motion of charged particles, channel the flow of gas, and influence the process of star formation. The fields are generated by electric currents flowing through the ionized gas, and they evolve and change over time as the gas moves. Light fills the space between stars as well. Starlight, of course, but also light from other sources. The gas itself glows faintly, emitting light as electrons and protons recombine to form hydrogen atoms. Dust grains absorb starlight and re-emit it as infrared radiation. There is even a faint background glow from all the distant galaxies scattered throughout the universe. And there is sound, of a sort. Pressure waves traveling through the gas, generated by supernova explosions or by the expansion of gas around hot stars. These waves are far too low in frequency for human ears to detect, but they carry energy through the interstellar medium, stirring the gas and triggering the collapse of clouds into new stars. So the space between stars is not empty at all. It is full of activity, full of substance, full of processes that connect one star to another and shape the evolution of the galaxy. It is the background against which everything else occurs, the stage on which the cosmic drama unfolds. Globular clusters and ancient memories. Surrounding galaxies, orbiting far above and below the main disk, are ancient cities of stars called globular clusters. These are some of the oldest structures in the universe, collections of stars that formed when the universe itself was young, over 13 billion years ago. Each globular cluster contains hundreds of thousands of stars, sometimes more than 1 million, all packed into a spherical region only a few hundred light years across. The density of stars in a globular cluster is much higher than in the galactic disk. If Earth were located in a globular cluster, the night sky would be filled with thousands of stars brighter than the brightest stars we see now. The sky would never be truly dark. The stars in globular clusters are old, among the oldest in the galaxy. They formed in the early universe, before the Milky Way had fully assembled, when the raw material from which stars form was less enriched with heavy elements. These stars are metal poor, as astronomers say, meaning they contain very little of any element heavier than helium. This lack of heavy elements tells us something about the conditions in the early universe. The first stars, the ones that formed when the universe was only a few 100 million years old, were made almost entirely of hydrogen and helium. There were no heavier elements yet because those elements had not been created. Heavy elements are made inside stars, through nuclear fusion, and released into space when stars die. The stars in globular clusters represent a second or third generation, formed from gas that had been slightly enriched by the deaths of earlier stars, but not by much. Globular clusters orbit the galaxy on elliptical paths that take them far from the galactic plane and then back again. Some orbits are nearly circular. Others are highly eccentric, carrying the cluster out to distances of hundreds of thousands of light years before returning. The orbital periods are long, tens or hundreds of millions of years, but the clusters have been around long enough to complete many orbits. There are more than 150 known globular clusters orbiting the Milky Way. Some are relatively nearby, visible to the naked eye as fuzzy patches of light. Others are more distant, discovered only with telescopes. And there are likely more clusters that we have not found yet, hidden behind the dust of the galactic plane or simply too faint and distant to have been detected. The clusters are slowly evaporating. Over billions of years, gravitational interactions between stars in the cluster occasionally give one star enough energy to escape. These escaped stars wander off into the galaxy, while the cluster gradually shrinks. Eventually, billions of years from now, the clusters will have dissolved completely, their stars scattered throughout the galactic halo. But for now, they remain ancient and stable, moving slowly through space on their ordained paths. They are time capsules, preserving information about the early universe, about the conditions that existed when they formed. By studying globular clusters, astronomers can look back in time, learning about the history of the galaxy and the universe itself. If you could visit a globular cluster, Traveling inward from the sparse outer regions toward the dense core, you would see the stars growing closer and closer together. The sky would fill with light. Navigation would be tricky, with so many gravitational influences tugging on your spacecraft. But it would be a gentle place despite the crowding. The stars are old and stable, past the drama of their youth, settled into quiet middle age. They will shine steadily for billions of years more. And perhaps, on a planet orbiting one of those ancient stars, someone might look up at their crowded sky and wonder about the larger galaxy beyond. They might see the Milky Way as we see it, but from a different angle, from a great height above the disk. To them, the galaxy would appear face on, a beautiful spiral spread out below, slowly turning. And they might wonder, as we do, what hidden things lie within that distant structure. What quiet mysteries wait in the spaces between the stars. And so we drift back from our journey, having explored just a few of the hidden things inside galaxies. The quiet spiral arms, the stellar nurseries, the invisible dark matter. The wandering stars, the sleeping giants, the rivers of light. The spaces between stars, and the ancient clusters that remember the beginning. There is so much more we could explore. So many more layers to peel back. But these are enough for tonight. Enough to give you a sense of the richness hidden within these cosmic structures. Enough to help you drift gently towards sleep. Galaxies are patient. They will still be there tomorrow, and the next day, and for billions of days after that. They will continue their slow turning, their gradual evolution, their quiet existence in the vastness of space. And you can rest now, knowing that somewhere out there, in the gentle darkness between stars, the galaxy continues its ancient dance.